Right. Hello, everyone. I hope you guys have a good time today. Okay. My name is Jeremy. I'm here to talk about the AWS Glue Iceberg optimizations. It's actually a very long form to answer your questions about the optimization. So in this talk, I'm going to start talking about what Glue is. And I'm going to give you a very quick overview of the Glue Iceberg optimizations. When I say Glue Iceberg optimization, what I really meant is the Iceberg maintenance. But in all our public documentation, we actually say Iceberg optimization. So here I just use two words interchangeably. And the second part of the talk is that I'm going to just do a very quick deep dive on the three optimizations we support today. We have compaction, we have snapshot expiration, and we have open file deletion. And then I will spend majority of the time just talking about some of the modifications we made on top of OSS Iceberg maintenance code base, mainly to solve some of the performance issues and some blocking issues for us to launch the optimization. And then lastly, I will talk about the future. I won't be able to talk about some specific projects or releases, but I will talk about some of the stuff we're thinking about on a high level. And then we'll talk about some of the stuff we would love to see and collaborate with the open source community. So before I talk about Glue, I want to talk about myself. So I'm Jeremy. I'm a principal engineer at AWS. I've been at Amazon for a little bit more than 10 years. I spent the first 9 years at the retail, building on different data processing systems. So far, my entire career has been all about working with data. So I love data. I love analyzing the data. I love building a lot of different analytic solutions for the customers. Now going back to AWS Loop. Just out of curiosity, raise your hand if you have ever used Loop before. Nice. That's very good. Very good. Very happy about that. So I'm just going to quickly go over the Glue because the audience knows everything about this. So what is Glue? Glue is a serverless data integration service that makes it easier for customers to discover, prepare, move, integrate the data from different sources. Once you have the data in Glue, you can use it for analytic purpose, machine learning, and application development. And over the years, we actually built a lot of different products and features under the Glue umbrella. So we have a data catalog, we have a Glue ETL, we have a data quality check, we have a crawler, and we have a stats collection. And the Iceberg table optimization is just one of the features or one of the products we recently released under the AWS Glue umbrella. So we have a bin packing compaction, which was launched last year. And a couple of weeks ago, we launched the snapshot expiration and open file deletion. So as a customer, how do I use this? Let's assume you have your Iceberg table registered in Glue catalog, and you want to enable optimization on the UI. What you can do is that you can go to the AWS console, locate your Iceberg table, and when you click the Iceberg table, you can actually see this UI on your console, and then you can go to the table optimization and click the enable optimization, which takes you to this page where you can enable all three of them or any of the optimizations, and you can choose the default value or your customer settings. When you choose the default value, we just run optimization using the table properties. If you do customer settings, then it will use your setting will take the precedence over the table properties. And let's do a deep dive on all three optimizations. Once you enable optimization, you actually can go to your AWS console and see all the job history. And one thing we noticed is that we mentioned something called DPU or DPU hour. So what is DPU? Anyone knows? DPU, yeah, data processing unit. So it's an abstraction over the number of CPUs, number of the memory size, and then the disk space. So the reason we mentioned DPU is because all these Glue optimization jobs actually running on Glue ETL. And Glue ETL essentially is a serverless Spark-based solution where you author your Glue script and you call Glue ETL API. It will launch the serverless environment for you, execute your job, and once your job is done, it will tear down the environment for you automatically. So it's quite easy to use. For snapshot expiration and open file deletion, they are schedule-based. So once you enable them, it will run once a day, and the next day it will run again to take care of maintenance table for you. But compaction is different. Compaction, we say, is entropy-based. So what does it mean? Entropy is, when we say entropy is actually a value we use to represent how many small files in a given partition. Entropy calculation is something we have built outside of the OSS compactor. So what happened on the hood is that we listen to the table changes or notifications from the Glue data catalog. And every time there's a data notification from Glue catalog, we will trigger this entropy calculation. And we only kicks off the compaction job if there are partition have a high entropy value. And we only compact those partitions. The reason is very simple. We don't want to compact the entire table because that will be very expensive and wasteful. The other interesting thing I want to mention is kind of a little bit history of, for this compactor is that initially when we launched the compactor, we actually used a C++ based solution. The reason we do that is because before we launched this product, we did some benchmarking and we realized that the out-of-the-box open source Spark-based compactor does not actually perform very well on the tables with lots of small files. And we do have lots of those customers. The C++ compactor still uses a majority of the code from the bin packing data rewriter logic from the OS code base, such as identifying which files to compact, to select for compaction. But the actual compaction is actually done using our own C++ code base, which combines the small file into larger files. But it's not the end of the story. The story is that after we launched this, we actually realized that there are some limitations with our C++ based compactor. One of the biggest limitations is that our compactor only supports the target file size up to 64 megabytes. And our customer actually want us to support larger target file size, such as 500, 512 megabytes, or even 1 gigabyte. Due to other reasons, we decided to migrate this C++ compactor to the OS compactor. But this migration actually requires us to solve some of the performance issues I just mentioned. So that's why we decided to make some modifications to the OS code base to mitigate those performance issues. So I'm going to talk about 3 different changes we made on top of the OSS Iceberg optimization. Not all changes are available in the OSS code base today, but we do have a plan to send out pull requests and merge them in the future. The first one is about how do we import performance for tables with a lot of small files. And this actually has something to do with the file open cost. File open cost is a value we pass to the OS's compactor. And today, if you look at the Iceberg code base, this file open cost value is always set to 0 and doesn't really allow callers to override it from outside. When with file open cost set to 0, each Spark task can take as many as small files as possible, as long as their estimated combined size is less than target file size. But this can actually hurt performance. One example I can give here is that imagine you have a table, have 100,000 small files, and each file only have a 1 kilobyte size. What will happen if you run the compactor? The Spark decide that it only needs one task to read all 100K files and write out 100 megabyte file. But on the other hand, the compactor will be much more performant if it can have multiple tasks. Imagine what if we have 5 tasks? Each task can take 20K small files. And at the end of the job, we will have 5 smaller files. Each file will have a 20 megabyte. So why does it have anything to do with the file open cost? So you can think of file open cost is a way to penalize having too many small files being added to a single Spark task. So the solution is very simple. We made a change to set the file open cost to a different value. And this value actually is calculated based on the estimated workload and the number of files in each Spark task. And the reason we don't do that, we don't override this value for every compaction job, is because with this change, the actual size of the output file will be much smaller, because previously the output file size will be 100 megabytes, but right now it will be like 5 of them, each with 20 megabytes. This is actually not a problem for us, because we have an entropy calculation, because every time you do a commit, we'll receive notification from glue data catalog. And once we receive notification, the entropy calculation will kick in, and we will automatically calculate the entropy for each partition. And if we do see that partition still have a very high entropy value, and we will kick off another compaction job, but only this time, the second compaction job will work with less number of large files. So even though it's an extra job, the overall cost combined and the runtime those compaction jobs will be much lower. And we did a benchmark, and we realized that this change actually leads to 5-time performance improvements for the tables with many, many small files. And for this one, we haven't submitted a pull request yet, but we do have a plan to do so. The second one is about how to prevent infinite compaction runs. So it might be very confusing for you, like why do we have this issue? Let me just deal with an example. Imagine you have one very small table, have 2 files. The first data file only have 50 kilobyte size, and the second file is also a 50 kilobyte size. And imagine the customer saying that, let's set the target file size to 99 kilobyte. What will happen is that when we launch a compaction job, the Spark job will create 2 tasks, and each task only take 1 file, and write 1 file. So overall, we will get a new snapshot with the same number of files. Essentially, this compaction job is not doing anything useful. And why is that a problem? Remember, we have an entropy calculation. So when the first compaction job does a commit, and the entropy calculation will kick in again, and the seed table on that partition will still have a very high entropy, and it will kick off another job again. So it's going to be an infinite loop for us. And you might wonder, this might be a very contrived example. How many tables actually have this problem? And the fact is that with larger than compaction job running, with all this different customer give us different tables to optimize, and we do this issue happen in production. So how do we actually solve that problem? So in OSS code base today, there is a method called plan file groups method that takes a list of file scan tasks, and it does some, it removes some of the ineligible scan tasks. For example, some tasks might be for a larger file. So for this file, we don't actually want to compact them. And after doing this filtering, it will assign them into a different file group, rewrite groups. And what happened right now in this example is that it will create different rewrite groups, and each rewrite group only contains one input file. So that's why the compaction run won't do anything useful. And the solution is actually very simple. We modify the plan file groups method to remove those rewrite groups that only have one input file. For this one, we also haven't sub with the pull request either, but we will do that in the future. So the last change I will kind of describe is how to improve the file listing for open file deletion. For this one, we actually do have a pull request, but actually there's a bug in it, so please don't use that. We will definitely put another revision and fix this issue. So what's happening today is that in today's OS code base, the open file deletion will find the open files recursively using the file system. But this is actually implementation, even though it works, it has two problems. The first one is that there is a much more efficient solution out there. So our customer store their data in S3, and we can simply leverage S3's list object API to list all the files with a prefix. The second one is actually a blocking issue for us. You remember when I showed the UI, when you set up the optimization, we actually ask you for IAM role. Because the reason we do that is because during the optimization job, we actually assume the IAM role to get a temporary security credential. And we use that credential to access customers' data in their S3 bucket. And this is all done through our own customized client factory and the credential providers. So the file system itself won't have access to those credentials. And the fix is actually really simple. The fix is just to use our own S3 client with the correct credential to do the file listing. So I just talked about three of the changes. So what is next for us? What would we like to see in OSS Iceberg? And what would we like to collaborate with the community? So the first thing we want to do is that in AWS, we continuously improve the price performance for our customers. That's why we spend a lot of time and energy on finding different ways to improve performance, lower the cost for customer. One example could be that we spend lots of time trying to understand how to handle small files, and we use an entropy-based solution to minimize the partition a compaction job needs to touch. And of course, there are other optimizations I haven't mentioned here. And also, we do a lot of benchmarking to making sure we understand the price performance under different conditions. We look at the table with the different file sizes, different table size, different number of files, and the table with different schema. And we do all this different combination and do benchmarking on them. With those tests, we actually discover more opportunities to improve the performance. And we have other features in the pipeline to continue lowering the cost for the customer. So stay tuned. The other thing I want to touch upon is our thinking on durability and correctness. In AWS, we take durability and correctness extremely seriously because customers trust us to do the right thing on their behalf. And the last thing they want to see is us messing up their data. So the first step we took to ensure durability and correctness is to perform tons of testing. So beyond the basic unit tests and the integration tests, we have canary tests, we have longevity tests. The goal is to actually simulate customers' workload so that we can identify issues before they do. But we actually don't think that's enough at all. We also invest in preventing data corruption caused by rare situations. For example, what if we have a faulty CPU in the data center? What if we have memory error? Or we have a bit flipping error during network transmit? Just to name a few. This actually requires us to make further modification in our code base and the OSS code base to insert more validation, such as CRC check, or even build an independent auditor to verify the correctness of the system. And last but not least, we would like to explore how to use automated reasoning or formal methods to verify the correctness of the Iceberg transaction protocol and the implementation. Automated reasoning uses propositional logic and the math proof to verify the correctness of the algorithm. And very often in AWS, we use tools like TLA+, Daphne, or P, etc., to verify the correctness of the complex distributed systems. And I already noticed some members in the community actually started looking into this. And we would very much love to collaborate and bring more awareness to the community. That's it. Thank you for listening.
Thanks for the presentation.
Thank you.
I have a question about
Yes.
what is the hardest part about writing your own app?
The hardest part, I think, what is hardest part to running your own compactor? I think the hardest part is running for AWS customers. Like, I think there are lots of concerns we have on durability and correctness, because this is a open source code. I'm not saying that open source code is not good enough, but we want to have an extra layer of security and the correctness check on top of that. I think that's one thing. The other one is that there are lots of different AWS customers with different table size, different workload, different requirements. We have streaming use cases, we have a batch use cases, and we found some of the scaling issue when you have a loss of, when you have very high frequent commits to Iceberg table. So I think that's a challenge to be able to deliver a very good price performance under all the different conditions for the customer is a huge challenge for us.
Okay, what are some of the best practices for running the table cases? That use and sort of what mechanism, what sources then it goes better for measuring sizes or
so what's a different the question is what's a good practice to run your compactor? I think it depends on who is your customer. If you're a customer, I think what they want you to understand what's the workload of your customer, and you should tailor your solution towards that situation. For us, it's a really different story because we have so many different customers, so we have to be able to spend lots of time craft our own data to making sure we have a good price performance. But you should look at your customer and try to understand your workloads, your requirements, and then making sure you deliver the price performance of what they want. The second question is about entropy. What is entropy? So entropy is just a value that we use to measure how many small files we have in partition. To be honest, I don't think that's good enough. We need more signals to understand when to run compaction, how to run compaction. Some customer tell us that our entropy is not good enough, it's not accurate enough. So this is something we are trying to improve.
Okay. So my question is, what other engines in Amazon support optimizations? I think Athena does.
Yes.
Redshift as well.
Redshift doesn't.
Okay.
It doesn't optimize Iceberg tables.
Okay, and then so how does a customer decide whether to use Athena versus these glue jobs to do the optimization?
I can repeat the question. So how does the customer decide when to use Athena to do optimization, when to use Glue to do that? So Athena doesn't, so if it was to use Athena, it's not a really fully automated or managed solution. So you have to go to the console, you have to analyze table, and you want to do that for you. This one, the Glue's optimization is fully managed. So it's just, you basically just set and forget. You go to console, you turn on optimization for snapshot expiration, open point deletion, we run that every day for you. For compaction, we look at the entropy and we automatically launch the compaction for you. So it's an easier experience for customer.
What about the online implementation? Bin hacking, Z ordering, is it?
So today we only support bin packing, and we are looking into other sorting or Z sorting. So does that answer your question?
What about, does Athena support Z ordering?
I think Athena essentially allows you to invoke the underlying Spark library. So I'm not very sure.
Yeah, so there was a question on the WebEx, I'm just repeating it. So one of our customers currently don't use Glue Data Catalog for Iceberg. They currently have a Hive catalog. They're wondering if they can use Glue Data Catalog for just automated table maintenance while keeping the current Hive's catalog set up in place. Is this possible or recommended?
So we actually thought about this, and
Can you repeat it?
the question is, if you don't have Iceberg table today, but you have a Hive catalog, and can we do any optimizations? I think the biggest concern for us to support that is how do you do transaction? How do you making sure when you do the compaction, you're not conflicting other read and writes? Iceberg is very nice because it has snapshots, it do validation before you commit. Even for rewrites, it does the validation. But if it's just Hive table, how do you do the validation? How do you making sure, what if I have ongoing compaction running, but customer decide to delete some data? Then how do I making sure that that deletion actually can reflect in the final results? So I don't think there's a good solution here, at least today. Yeah.
Can you share with us perhaps some of the risks you're worried about for the extra durability testing that you're pursuing? Like, for example, when you listed things of like new failing or something like that inside the data center, wouldn't that be the purpose of the orphan files to help make sure that the transactions are atomic and wouldn't affect the durability? Maybe if you could share some of the risks that you're concerned about, the community could help close those gaps as well.
So what are the specific concerns I have in terms of durability and correctness? So it's not really about there I think there are two issues. First one is that what if there's 40 CPUs? What if there is a memory error somewhere? And let's say the compaction job can write 40 data. Like it reads some data, but it's write incorrect data, and there's no other solution out there to just verify what you write is actually what you read. Right? So it is a very rare scenario, but in some sense it can happen. The other one is that how do we verify the correctness of the transaction? Is that the question? So I do worry about that because sometimes at Amazon we look at the distributed algorithm. We always use like TI plus to verify the correctness, and we have like folks in AWS actually build like P observer to always observing the correctness of the system. So this is something we want to kind of influence the community to look into, especially this is a very like critical path of code. So yeah.
And so it's less about the transactionality, more about the data correctness from reading and the TLS part, the TLA.
TLA plus.
Yeah. You probably read up Jack that 90.
I did.
Okay.
Yeah.
Good to share.
Thank you for speaking. I want to question about the next step of and are we considering something like the master recovery for your like an application across the weeks?
So I can't tell you more about this because for confidentiality, but there is some thinking about that. For example, you could set up S3 replication that you can replicate from one bucket to another bucket. And of course, there's a concern, whether because the metadata only doesn't really change the path, right? So Kevin actually mentioned that it's a location provider. So you could write your own location provider to swap out the bucket name. So what S3 gives you is that you can copy from bucket A to bucket B, and the path will be same. Only the bucket name will be different. So what you can do is that when you read the manifest, you can actually replace, somehow set the flag saying this is the old bucket, is the new bucket, and you replace all the bucket name when you read the data. So that's one solution.
think that we integrability of we see is like the root.
I think so the question is this a glue feature or is the community should support that? I think it would be much simpler if community can provide an easy way for us to replace the bucket or pass the data file pass in the metadata. Otherwise, they have to do those, write our own location provider and replace the bucket name, which is kind of hacky to me.
Thank you.
Okay, so I have one question for the ETL platform when you're using it for speech domains. How do you trade it as a community to use those shelves with that? Also, one of the things like we're able to share with a lot of people are like when you come like Snapshot Expiration or what about this memory seen?
I would say what is the largest table? I can't tell you. Terabytes easily could be. We have lots of big customers. So what was the first question? How do you do glue ETL?
So for the ETL job, we have the service list job to run.
Right.
And, we have a map. So for that job, we don't know like what's the snapshot expiration. Snapshots.
Yeah. So how do we set up to making sure it scales? Is that the question? So the nice thing about glue ETL is that it does support auto scaling. I believe it's actually look at the actual number of tasks that outstanding task in the glue, and it decide to give more DPU or lower the DPU. So that's one way we kind of rely on glue to scaling. So scaling. The other thing is that we make additional code change in the OS code base to limit number of files we need to delete. So there is a certain points that if over that threshold, we're just gonna stop deleting those files and wait for the next job run. The main reason is really just about making sure that the fairness of the DPU usage, because it's a multi-tenant system, so we want to making sure that there's no limits the noisy neighbor effect.
Any final questions?
There's a lot of interesting questions.
Okay, I guess, yeah, that's last session for today's. Thanks, yeah.
Okay.
So, yeah, thank you. Let's get in. No, we're eagerly waiting for me to bring up the slides. So just a couple of things. We're doing this more often going forward. We have few planned. There's one planned for next month in the Bay Area. So if anyone's there, you can watch out and join us. It'll be in Luma. We're also planning in New York, Munich, and somewhere in more exotic places like Singapore if possible. But we'll be coming back to Seattle as well and coordinating with our partners here, Snowflake, Databricks, and others who've shown interest. There's some slides at the back. While you're walking out, you can pick it up. AWS folks in the room, please do not touch it. It's not for you. And there's more pizzas, and we'll be here for another hour or till the security kicks us out so we can party. Yeah, thanks for coming in today. Really appreciate it. And yeah, we'll stick around and we'll talk more. Thank you.